So we mentioned before that just fitting our training data was not enough to be doing machine learning. In machine learning, we're really interested in generalization. Let's dive into that topic a little bit more. So here we've got a data set where we've got some spam examples here on the left and some not spam examples over on the right. If I wanted to, I could try and fit a linear model to sort of disambiguate the spam from the not spam. But any sort of linear model that I would try and fit here would end up making a little bit of error. Maybe this guy would be misclassified, or that guy would be misclassified as being on the wrong side of the line. And I might decide to try and be clever and get 100% accuracy on my training data by drawing a more complicated line. Maybe it would look something like this. I'm going to go and make sure that my model is going to be super clever and get 100% accuracy. All of my training examples are now completely correctly classified. What's the issue here? Well, the issue is, what if new examples are coming in? I might end up with some new examples that the model is just not really well suited to doing a good job on. So in a sense, this model has maybe overfit our training data originally, and it doesn't do a good job of classifying new, previously unseen data. Okay, so we've seen that if our models are too complicated, that overfitting is a real problem. How can we make sure that our models are not overfit in practice? Well, let's step back and take a look at the big picture of what it is we're trying to do in machine learning. At a very abstract level, we can imagine that there's some hidden process that is giving us data. And that hidden process might be something like the process by which emails are generated as either spam or not spam, and people label them as such through their perceptions, or the process by which pictures of puppies are generated and people label them as cute or non-cute. The process could be anything that gives us data, and in general, we're not going to know the full details of that process. The only thing we're going to know is the concrete examples that we get to sample from that process. So specific pieces of email or spam, specific pictures of puppies. We call those samples our data samples. Now, ideally, we would like to be able to train on a data sample and then know that it's going to do well on new draws from that hidden distribution. How will we be able to trust that? Well, one thing that we could do is we could use some nice ideas that go back as far as William of Ockham from the 14th century, our first machine learning theoretician, who developed the idea of Occam's razor, basically saying that a model should be as simple as possible. There's a whole field around this called Generalization Theory, and it's a fascinating field. We're not going to get into that too much in this course because we don't have to use theory. We can, in fact, use empirical stuff. And the empirical strategy we can use is to take another draw from that distribution and see how well we do. This is called using a test set methodology. So we pull one draw of data from that distribution, we train on that, that's our training set. We take another draw of data from that distribution, we call it our test set. And if we do a good job, about as well at predicting on our test set as we do on our training set, then we've got pretty good feeling that our model is going to be able to generalize well onto new, previously unseen data. Now, there's a couple of caveats here. This is sort of the fine print of machine learning. The first is that we are drawing our data, are drawing independently and identically from that distribution. We're not biasing ourselves in any way. The second is that distribution is stationary. It doesn't change over time. And the third, kind of implied here, is that we're always pulling from the same distribution. We don't suddenly start pulling from a different one. Now, those are critical assumptions, and they sort of form the bedrock of a lot of what we do in supervised machine learning. But in practice, sometimes we do violate them. The stationarity assumption might be violated if, say, user behavior on shopping changes over the holiday season versus in the summer. And the pulling from the same distribution might change if people suddenly decide that a different breed of puppies is cute than they saw before. Fashions do change. So it's important for us to be aware of these assumptions and also to pay careful attention to our metrics anytime we know that these assumptions might be violated.